Welcome back to our networking series part 3. In today's interconnected world, maintaining network security is crucial. In this video, we will explore the roles of firewalls and network ports, two fundamental elements that control and protect data flow within networks. We will examine how these components operate to safeguard systems, ensuring that only authorized traffic passes through while blocking potential threats. We will start with a quick overview of the 7-layer OSI framework that guides how data is transmitted over networks, a basic explanation of network ports and their role in enabling communication between services and devices, an approach to segmenting a network into distinct security zones with specific access rules between them, packet filtering firewalls that filter traffic based on IP addresses and port numbers, managing routing and connection security. Application firewall that inspect data at the application layer, allowing more granular control based on specific application level traffic. Explain the difference between firewall that track active connections and those that treat each packet independently for network security management, a security technique that divides a network into smaller segments to minimize attack surface and improve granular security control, a method of mapping private IP addresses to a public IP address, allowing secure communication between internal and external networks. To proceed, it is important to first get the overview of the OSI model, a framework that explains how data travels from one device to another across networks. The OSI model is divided into 7 layers, each playing a specific role in the communication process. The physical layer is like a city's infrastructure, transmitting data through electrical signal, light pulses, or radio waves, ensuring data moves between devices within a data center or across external networks. The data link layer manages data flow within the same network, like traffic lights using switches and NICs. It directs data to the correct device by recognizing MAC addresses, ensuring proper delivery. The network layer functions like a postal service, directing data packets using IP addresses, router forward packets between servers, external systems, or clients, ensuring communication across the internet or subnets. The transport layer acts like a delivery service, splitting data into segments and ensuring it arrives intact using TCP UDP ports. Network ports direct data to the correct services on the receiving device. The session layer manages ongoing communication, keeping session active and organized during video calls, file transfer, or between application and servers, ensuring smooth data flow and maintaining persistent connections. The presentation layer acts as a translator, converting data into formats application can understand. It handles encryption and decryption, ensuring secure transmission and proper decoding of data like images or secure server information. The application layer is where users interact with network services like web browsing, email, and file sharing. Applications like Chrome and Outlook enable access to cloud services like Salesforce and Office 365. Now that we have completed the overview of the OSI model, let's move on to the next topic, network ports. Imagine this building represents a device on a network like a server, computer, or a VM. The building has a single address, much like how every device on a network has a unique IP address. This IP address is how other devices identify and locate it. But just as the building has multiple doors, each door leads to a specific part of the building, and only authorized people can enter certain doors. In the same way, a device such as a server, computer, or a VM with an IP address has multiple network ports. Similarly, each port on a device handles a specific type of network traffic or services such as port 80, port 403 handling web traffic, port 25 for email port 3389 for Windows connecting through a remote desktop, port 22 for the SSH communication. Let's see one of the example. Network ports are essential in enabling communication between different services in a three-tier web application architecture. Each tier, web app and database, has its own IP address and uses specific ports to communicate with each other. When a user accesses a web application, their request is sent to the web tier on port 443 or 80. The web tier forwarded this request to the app tier on port 1234 where our application is running, which processes the data. In this example, the web tier has an IP of 192.168.10.14 and the app tier has an IP of 192.168.20.24. Once the app tier processes the request, it may need to query the database. The app tier communicates with the database tier using port 3306 for MySQL database or port 1433 if the database is Microsoft SQL. In this case, the database tier has IP address 192.168.30.34. In summary, network ports are crucial in facilitating communication between the web tier, app tier, and database tier in a three-tier architecture or any other services running. By using specific ports like 8443, 1234, 3306, and 1433, data flows seamlessly between the tiers, enabling efficient application functionality. Now, in this setup, there is no security in place. Let's move on to the next topic, firewall. We will see how we can secure the communication. A firewall acts as a gatekeeper, allowing or blocking traffic based on predefined security rules. It is essential for both enterprise and home network to prevent unauthorized access and protect sensitive data. It can be installed as a physical appliance, host base, or configured as a virtual machine within an organization infrastructure inspecting all traffic. In our previous example, there was no security. This user could potentially be a hacker or malicious actor from outside who could enter the network and cause damage. To enhance security in this setup, architecture is divided into zones with the external zone outside the organization and the DMZ as a buffer. The DMZ securely hosts public services while protecting internal resources like app, database VMs, and services. Imagine an airport. The public area is like the external zone accessible to everyone, including check in counters and restaurants. The secure internal area is restricted housing, boarding gates, and runways, accessible only to authorized personnel and passengers who have cleared security. Checkpoint act as the DMZ, a buffer between the public and secure areas, just as the DMZ protect internal resources in networking. The checkpoint ensures only those who pass security enter the secure airport zones. To protect the internal network, firewalls are placed between the DMZ and internal systems. We harden system by installing only essential program and disabling unnecessary services, reducing potential attack surfaces. With firewalls between the external network and the DMZ, these firewalls serve as the first layer of protection, filtering incoming traffic from the internet before it reaches the web server in the DMZ. With hardened systems and a firewall between the DMZ and the internal network, traffic within the internal network is only allowed from certain subnets, VLANs, and specific ports between VMs, in our case, app and DB. Even if a DMZ is compromised, attacker cannot reach the internal network or other services running. The firewall and system hardening block unauthorized access, ensuring internal resources remain secure. Now that we understand the DMZ, internal network, and firewall, let's examine packet filtering firewall at layer 3 and layer 4. These firewall inspect packets based on IP addresses, ports, and protocols enforcing traffic rules. At layer 3, firewall act like a postal worker who checks only the address on an envelope. It inspects the source and destination IP address on data packets and decides whether to allow or block the traffic based on these addresses. Just like mail that gets routed based on its address, Layer 3 firewall ensures that only traffic with valid IP address is allowed through. A Layer 4 firewall works like a postal worker who checks not only the address on the envelope but also the service label, example letter, package, business document, indicating what type of communication it represents. The firewall inspects IP addresses and port numbers just as the postal worker routes letters, packages, or business documents based on their content type, web traffic, email, file transfer are routed to the appropriate service based on the port number. We have defined a rule that only traffic on port 443 to IP address 192.168.10.14 will be allowed from the external. Any other traffic will be denied. Rules are processed from top to bottom. Now, for the firewall between the DMZ and internal network, we define a rule that only allows traffic on port 1234 from IP address 192.168.10.14 in the DMZ to destination IP 192.168.20.24. A layer 7 firewall, also known as an application layer firewall, inspects the content of the data packet just like a postal worker opening an envelope to check what's inside. It examines the actual data, whether it's a web request, email, or file transfer, to detect and block harmful content. For instance, it can block malicious script hidden inside an HTTP request or identify harmful attachment in an email. Layer 7 firewall use signature based detection. This involves comparing network traffic to a database of known attack signatures such as SQL injections, malware patterns, or cross site scripting attacks. If the firewall detects a match with the known signature, it blocks the malicious traffic before it can reach your server, ensuring the safety of your applications and data. A stateful firewall tracks and remembers the entire connection. When you send an HTTP request to a web server, the firewall logs the session and check and send it to the web server, allowing the return traffic back to your device automatically. This is like a two-way street where once your request is made, the firewall knows to expect a response and doesn't need to check each packet again. Imagine ordering food at a drive-through. Once you have placed your order, the cashier expects you to come to the window to pay and receive your food. Similarly, the stateful firewall tracks the session, allowing the response traffic like your food back to the original requester you without rechecking the details. A stateless firewall doesn't remember connections. When you send an HTTP request, the stateless firewall checks each outgoing packets based on predefined rules and sent to web server. When the web server sends a response, the stateless firewall recheck each return packet individually, and if it's new, even though it belongs to the same connection, there is no memory of the session. Think of this as going through the airport security every time you enter or leave, even if you pass through security once. Each time you return, you have to go through the process again. Similarly, the stateless firewall treat every packet like a separate entity, reapply rules even for returning traffic. Let's suppose we have three applications running across three tiers: App 1, App2, and App3, with each tier having its own subnet and VLAN configured. Previously, we used a firewall to manage communication between different networks or VLAN. Now, with microsegmentation, VMs to be protected within the same tier by ensuring that App1 web server cannot see or communicate with the web server of App2 or App3 even though they are in the same network. The same rule apply for App1, App2 and App3 across all tiers, isolating their traffic within their own segments. We are protecting at layer 2 because traffic between layer 2 not reaching router or firewall. In AWS, we use security groups are used to isolate traffic within the same subnet. For instance, you create a security group for App1 web tier that only allows inbound and outbound traffic from App1 app tier and restrict traffic to App2 and App3. To protect our private network for exposure to the internet of our IP address, we use network address translation. NAT converts private IP address into public IPs for internet communication, shielding internal devices from direct exposure while allowing secure interaction with external systems. SourceNet is used when devices in a private network like a home access the internet. The router or firewall translate private IPs like 192.168.60.80 into public IPs like 22.5.6.8, enabling communication with external systems while hiding internal network details. This is the private IP of my laptop, and when I connect to the internet, my private IP is translated to a public IP 41.122.166.5 at the router. On the internet, no one knows my private IP, only the public IP is visible. This is known as SNAT, source netting. In DNAT or destination NAT, user from internet trying to access the web server, the process involves modifying the destination IP address in the packet header as it passes through the public firewall. The public IP 202.5.6.7 is replaced with the private IP 192.168.10.14, ensuring that the traffic is correctly routed to the internal server while protecting the internal network structure. And that's it. We have completed the section on ports and firewalls. In the next video series, we will dive into switch and router configurations, VLANs, and troubleshooting for setting up a networking infrastructure. If you found this video helpful, don't forget to like, subscribe, share, and leave a comment with any question. Thank you for watching and happy networking.